So next we're going to talk about vectors in three-dimensional space. So a vector v in three-dimensional space can be represented in two different ways. The first one is in the component form, but now you have to be careful because we are in three dimensions. So the vector consists of three components. The first component, let's say it's going to be v1, the second component is going to be v2, and the third component is going to be v3. There's another way to present a vector in three-dimensional space. That is, this can be written in form of a standard unit vectors form. Okay, so the first way that we can represent a vector is in the component form. And it's written as v equal to v1, v2, v3. And also can be described in the standard unit vector form. So we have seen standard unit vector forms in the last lecture when you talk about the standard unit vector I for the x-axis and the standard unit vector j for the y-axis. In three-dimensional space, we needed the third standard unit vector for the z directions, and we're going to denote that as k hat. As you can see over here, you have the vector v in the component form of v1, v2, and v3, and that can be written in terms of the standard unit vector forms as v1 times I. In this case, this picture is from the textbook, so you don't it doesn't show the I hat or j hat or k hat for that matter, because they were able to write the letter in boldface. But for us, we're gonna write the notations with the hat to indicate that is the standard unit vector form. So v can be written as v1 times I hat plus v2 times j hat plus v3 times k hat. Again, k hat is the standard unit vector form for the z directions. Now, to determine a vector in three dimensions given the initial point and the terminal point, we're going to perform a very similar calculations as we did for the case of 2D two-dimensional vector. That is, given the initial point of P equal to x1, y1, and z1, and the point Q, x2, y2, and z2, we can calculate the vector PQ as follow. That is x2 minus x1, comma y2 minus y1, comma z2 minus z1. And these calculations can be done because the vector or the requirement, as you can see, is PQ vector. So P first indicate that is the initial point, Q is second, that indicate the terminal points. If you swap the point Q and P and find the vector QP, that's going to have a different result at the end. Now, when you calculate the vector PQ, you get the resulting vector in form of x2 minus x1, y2 minus y1, and z2 minus z1. What you see in the picture right here is there is a vector v that's going to be parallel to the vector PQ, and this vector v has an initial point at the origins and the terminal point at the value v1, v2, and v3. And in fact, that v1, v2, and v3 corresponding to x2 minus x1, y2 minus y1, and z2 minus z1. So again, this vector is the vector PQ, and this vector right here in black is called the positions vector. The position vector is the vector starting at the origins and parallel to the vector PQ. So this vector right here is also going to be the position vector for the vector going from the point R to the point S. So this idea is very similar to the one we covered in the last lecture. Um, Given 2 points, you can calculate the vector, let's say between P, the vector connecting P and Q, but the position vector is going to be the vector with the initial point at the origin and the terminal point equal to the resulting calculations of P and Q. So now let's move on to magnitude and let's revisit the idea of the unit vectors. For the magnitude of a vector, again, this is the three-dimensional case. So we have that the magnitude or length of the vector PQ equal to x2 minus x1, comma y2 minus y1, comma z2 minus z1. So this is just the setup when you look at the graph right here. It's certainly going to change depending on the problem, but for now the setup is that P is the point x1, y1, and z1, and Q is the point x2, y2, and z2. And to calculate the distance or to calculate the magnitude or the length of the vector, we're going to do the following. So the magnitude of the vector PQ is equal to the square root of x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. So this is going to be similar to the distance between the 2 points P and Q, even though PQ is a vector, but when you take the magnitude or the length of the vector PQ, it actually show you the distance between the 2 points. So for the unit vectors, again, you have seen that earlier already when you talk about how to write a vector in standard unit vector forms. So in this case, again, I want to show you the standard unit vector form for the x-axis is written in the three-dimensional vector 1, 0, 0. J hat is the standard unit vector form for the y directions or the y-axis, and is the vector of the form 0, 1, 0. And k hat is the standard unit vector for the z directions, and is written in form of 0, 0, 1. Now, we can perform different operations on the three-dimensional vectors, again, very similar to what we have seen in the 2D case. Given the vectors v and vector w, and also for the scalar k, the scalar multiplications can be performed as follows. So k times v is equal to k times v1, v2, and v3. To perform this scalar calculations, we just basically multiply k for every single term or every single component in v. So you have k times v1, comma k times v2, comma k times v3. And it depends on the value of k that you can make the original vector a little longer or smaller or turn it into the opposite direction. So this is the example of the scalar multiplications. In this case, I have the original vector v and the scalar c here. So when c is greater than 1, you make the vector bigger but still point in the same direction as the original vector v. When c is less than -1, you make the vector, the original vector, bigger, but you turn that into the opposite direction as the original vector. You can perform vector additions as follow. So you add two vectors together. So v plus w equal to v1, comma v2, comma v3 plus w1, w2, w3. And you perform the component wise. That means the first component get added together, the second component get added together, and the last component get added together, and we get the result as v1 plus w1 comma v2 plus w2, comma v3 plus w3. And again, similar to the case of two-dimensional vectors, there are two methods that you can apply to get the vector additions. The first one is the triangle method, and the second one is parallelogram method. In this case, I have a pictures for the case of parallelogram method, where you have two vectors, vector u and vector v. They have the same initial point, and when that is the case, when you do the vector additions, is form a parallelogram. So here is parallelogram method.
For vector subtraction,
Technically, what you do, you perform the vector additions on the opposite of one of the vector in the subtractions. So what do I mean by that? If you do v subtract w, is actually turn out to be v plus negative w, or v1, v2, v3 plus negative w1, negative w2, negative w3, and you get the result as v1 minus w1, v2 minus w2, and v3 minus w3. So these are the basic properties of vectors in a three-dimensional space. There are the properties that you see in the last lecture as well, including commutative properties, associative properties, distributive properties. Those properties can directly be applied to the case of three-dimensional vectors. Now let's move on to some example. Now for example 5, we want to sketch the vector PQ, where P is the initial point, 1, 2, and 3, and Q is the terminal point 4, 5, and 6. And I want to express the vector in component form and in the standard unit vectors form. We have been learned how to locate the point in space already, so let's try to do it again for this example, and hopefully at this point we are comfortable with locating the point in space. So let's start with the point 1, 2, 3. So for you have x equal to 1. So from the origin, you go into the positive x directions to 1. And from there, you're going to draw the line that's going to be parallel to the y-axis. And on the y-axis, you go to positive 2 and draw the line that is parallel to the x-axis. And the purple line and the blue line intersect at one point, and that point is 1, 2, 0. And then from the origin, you're going to draw a line connecting the origin with the point 1, 2, 0. And that line is in red. So this is the line segment with two ends, one at the origin, the other one is at the point 1, 2, 0. From the origin, you're going to go up to the z-axis by 3 units because z is equal to 3 in this case. And from there, we're going to draw the line that's going to be parallel to the red line segment. And from the other end of the red line segment, 1, 2, 0, you're going to draw a vertical line that is parallel to the z-axis. And the green line and the orange line are going to intersect at one point, and that point is the point that we're looking for, 1, 2, 3. So now we move on to the point Q. The point Q is equal to 4, 5, and 6. So again, we're going to follow the same procedure as we have done so far. We start with x equal to 4. So from the origin, we're going to go to the positive x directions to 4. And from there, you're going to draw a line that's going to be parallel to, I'm going to draw the line that is parallel to the y-axis. And on the y-axis, you go to y equal to 5, even though it doesn't show here in our axis, but I can assume that is somewhere in here. So this is 5. And we're going to draw the line that is parallel to the x-axis. I'm going to do that in purple. And the two lines, the purple line and the blue line, is going to intersect at one point, and that point is the point 4, 5, 0. And now we're gonna use red to connect the origin with the new point we just found. And this is the line segment. And we're gonna use pink to connect the origin with the point 4, 5, and 0. We have the line segment connecting these 2 points, right? So the line segment in pink has 2 ends. One is at the origins, the other one is at the point 4, 5, and 0. From the origins, we're going to go up in the z directions to 6, right? Because z is equal to 6 in this case. Even though it doesn't show here in our axis, but I can assume that 6 is going to be somewhere here. So let's do that. So you go to 1, 2, 3, 4, 5, and let's say this one is 6. And from there, I'm going to draw the line that is parallel to the pink line. And from the point 4, 5, 0, I'm going to draw the line that is going to be parallel to the z-axis, and the line going to intersect the orange line at the point, and that point is going to be 4, 5, 6. And you have the initial point, you have the terminal point. You can connect these 2 points together to form a vector PQ. And I'm going to use blue for that. Alright, so that's the vector PQ in 3-dimensional space. Now, you want to calculate or form the vector PQ algebraically and express the vector in the component form as well as in the standard unit vectors form. So to calculate PQ, to calculate vector PQ, you do 4 minus 1, 5 minus 2, 6 minus 3. And you get 4 minus 1 to be 3, 5 minus 1 to be 3, and 6 minus 3 to be 3. So that's the vector PQ. So this vector we just calculate is in the vector, is in the component form. Now we want to rewrite this in the standard unit vector forms. So this can be written as 3i hat plus 3j hat plus 3k hat. And that is the results that we're looking for. So let's move on to the last example of this selection note. So consider 2 points P of equal to 5, 3, and 1, and Q is equal to -7, 8, and 1. So hopefully at this point you're comfortable with locating the point in space, so I'm going to skip that and just focus on doing the calculations. Alright, so part A tell you to find the vector PQ with P is the initial point and Q is the terminal point, and then express it in the terms of standard unit vector form. So for part A, you get the vector PQ is equal to -7 minus 5, 8 minus 3, 1 minus 1. And you get this to be -12, 5, 0. And this can be written in the standard unit vector forms as -12 I hat plus 5j hat plus 0k hat. Because the last entry is equal to 0, is equivalent to writing the answer as -12i plus 5j. Okay. Now for B, you want to find the magnitude of the vector PQ. So the magnitude of the vector PQ can be found using the formula. So that is the square root of -12 square plus 5 square plus 0 square. If you do the calculations correctly, you're going to get a square root of 169, or this is equal to 13. Now you're going to find the position vector in part C of the magnitude 10 in the directions of the vector PQ. So again, I want to mention that the positions vector is the vector that is parallel to the vector PQ, right? Where the position vector, the initial point is at the origins, and the terminal point is at the point -12, 5, 0. So find the position vector of magnitude 10 in the directions of PQ. So what you do is that you're going to find the unit vector of PQ. So the unit vector of PQ can be calculated as, right, so you have U, right, to indicate the unit vector of PQ is equal to PQ divided by the magnitude of PQ. So you get the vector PQ to be -12, 5, 0 divided by the magnitude of PQ, which is 13 in this case. All you do 1/13 times the vector -12, 5, 0. And if you want to find the position vector of magnitude 10 in the directions of PQ, so what you do is, so the position vector that we're looking for is equal to 10 times vector u, or it's going to be 10/13 times -12, 5, and 0. And that is what you're looking for. So that's it for me for this lecture. Please let me know if you have any questions. Thank you.